Capacitance is the property of a circuit element that permits it to store a charge of electricity. A capacitor, also known as a condenser, temporarily stores an electrical charge and consists of two metal plates, separated and insulated from each other by a dielectric material. Dielectric is defined as a nonconductor with a specific amount of resistance against current flow. When one plate of the capacitor has an accumulation of electrons, the electrons on the other plate will be pushed away, so one plate will be negatively charged and the other plate will be positively charged. As an alternating current charge is applied to the capacitor or condenser, the negative charge on one plate will cause a proportional positive charge on the opposite plate. As the charge on the first plate changes to positive through the sine wave, the opposite plate will change proportionally to a negative charge. The unit of measurement is a farad, with small capacitors, often measured in microfarads, or 0.000001 farads. The symbol of microfarads is MFD. A capacitor, with a maximum amount of electrons, is considered to be charged. The surface area of the plates, the distance between the plates, and the dielectric material between the plates, are all factors that affect the capacitance of the circuit. When a capacitor is connected in series with an alternating current circuit, the current is allowed to flow back and forth in the circuit without actually passing through the capacitor. Notice, the electrons build up on one plate of the capacitor and flow out of the other plate. An electrostatic field is established that causes the current to flow in the opposite direction. However, as the voltage from the source begins to drop, the electrons starts to flow away from one plate of the capacitor and onto the other plate. The basic effect of a capacitor in an alternating current circuit is to cause the current to lead the voltage. If a circuit could be designed without any resistance, the current would lead the voltage by 90 degrees. This can be seen in the illustration for phase, by the way in which the electrons move through one alternation. Notice, as the voltage rises, the current begins to drop because of the dielectric stress in the capacitor. By the time the voltage has reached maximum, the capacitor is completely charged and no current flows. At point 1, the current has a value of 0 degrees. As the voltage begins to drop, the current flows out of the capacitor in the opposite direction due to the potential of the capacitor being higher than the potential on the line. At point 2, on the curve, the voltage has dropped to 0 degrees, and the current is flowing at a maximum. In the illustration, what is the total capacity in microfarads for 3 12 microfarad capacitors connected in series? In step 1, setting up formula, 1 divided by Ct E equals 1 divided by C1 plus 1 divided by C2 plus 1 divided by C3. In step 2, inserting values, 1 divided by Ct E equals 1 divided by 12 plus 1 divided by 12 plus 1 divided by 12. In step 3, applying formula, 1 divided by Ct equals 12 divided by 3, which equals 4. Therefore, the total capacity in microfarads is 4. For example, what is the total capacity in microfarads for 3 12 microfarad capacitors connected in parallel? In step 1, setting up formula, Ct, which is the total capacity, equals C1 plus C2 plus C3. In step 2, inserting values, Ct, which is the total capacity, equals 12 plus 12 plus 12. In step 3, applying formula, Ct, which is the total capacity, equals 12 plus 12 plus 12 equals 36 meters Fd. Therefore, the total capacity in microfarads is 36 meters Fd.